Hey biologists, Mr. Font here. Today we're going to be going over some of our calculations for water potential. So this is going to be from our practice worksheet here for water potential. Let's start at the top. Actually, I'm going to write in some of our equations. So as I mentioned, that AP is going to give you some of these equations. So you do not need to memorize these, although the big takeaway, of course, is to know what these equations, what they actually mean. So when you get to the final answer, you understand, oh, this is what they're trying to get me to answer questions about. So this first one is our water potential. So we need to add our potential of solute and our potential of pressure. These two values added together will give us our water potential. Additionally, there's one other equation that is going to factor in a few times is to calculate our solute potential, we have our negative I crit, I-C our T is going to be our second equation. So a few things about this. This T must be in Kelvin. Don't forget our value is going to be, just so we have this ready to go, 0.0831 is our R value. This is going to be our concentration, and this is the ionization constant, and we'll talk about those when we get to some actual examples. Anywho, so now we're ready to go once we have our equations and a few of our things identified. So question number 1 reads, if a cell happens to have a pressure potential of 3 bars, its solute potential is negative 4.5 bars, what is going to be the total or the water potential? So just like before, we need to use this equation, this top one here, so we know that our water potential is going to equal our solute potential, which we said was negative 4.5. And I'm going to leave out the units just so we can do the number portion. We'll get to the units in a moment. Plus is going to be our pressure potential, which told us it was 3. If we add the two of these together, don't forget this is a negative 4.5. We should get negative 1.5. Don't forget the units, as I mentioned, we'll come back to it, is bars. So we get to this as our total water potential. Number 2, we're going to use the same cell from question number 1. So this negative 1.5 bars is now going to play a factor. It's placed into a beaker of sugar water. It's placed into a beaker of sugar water. Mind you, it has the solute potential, this sugar water, of negative 4.0 bars. Which direction will be the net flow of water? What I think might help sometimes, I'm going to do a quick little doodle on the side just so I can visualize. Here's my wavy line to represent the water. Here's my cell floating around in that solution. And we already know that the cell, because we calculated in the first part, it says the cell from question number 1. We know that this value is negative 1.5. The question is, what is going to be the solution or the environment in which the cell is then residing in? Now, we know it gave us the solute potential, and as part of our equation, that's 1/2 of it to get to the water potential. What we're missing here is the pressure potential. If you recall from our notes, I mentioned that there are going to be 2 things that they are going to assume that you have memorized. They will not give it to you. And why I underlined that this is placed into a beaker that's sitting on your table in an open environment. This means that its pressure potential in this case is going to be 0. That is one of those values that they will not tell you. It is going to be assumed. So if we fill out our equation, we have our solute potential is going to be our negative 4.0 plus, because it's in a beaker sitting on a table in an open environment, its pressure potential is 0. Add the two values together. What it really comes to is negative 4.0. So in this case, when we have beakers sitting on tables in open environments in which the pressure potential is 0, the water potential actually is the solute potential. The two of them are synonymous. Now, if we were to close this beaker and make a closed container, then the situation would change. And that's going to be more so down below when we start to talk about real instances, like things like plant cells, for instance. They do not exist in an open environment. They're then in closed containers, i.e. cells. Anywho, so now we have our water potential outside is going to be negative 4.0 is what we get. So this negative 4.0 compared to the negative 1.5. Water wants to flow from the higher water potential to the lower water potential. And be careful, in this instance, we have two negative values. They're both negative. So the closer to 0 is truly the one that is the higher value. Don't just go with whatever number is bigger. So the negative 1.5 is the higher value. The negative 4.0 is the lower value. So from high, that's the cell, to low, it's going to move out of the cell and into the solution. So this would actually cause the cell to then shrink because of the movement of the water that's moving out of the cell. So that's question number 2. Question number 3 says a very similar type of thing. If we again use the same question from number 1, place it into a beaker of sugar water, we have that beaker, sugar water. Again, the pressure potential is 0 because it's sitting on your table in an open environment. We now have a new solute potential. It's going to change a little bit. In this case, you might notice they used a different unit. They did not use bars. In this case, they're using an additional unit we could use, which is MPa, or megapascals. Now, they're going to give us a unit conversion, so we're going to have to do this translation. If we're going to compare numbers, they must be the same unit. So we're looking at who has the higher water potential. They have to be the same unit. You cannot say, because one's in megapascals and one's in bars, you can't compare those numbers. So really, this question is a unit conversion. If you recall from chemistry class, I'm going to go ahead and start to do this conversion. Let's set it up using our giant plus sign here. In our upper left-hand corner, we're always going to start with our given. So negative 0.15. Don't forget your units of our megapascals. We need to cancel out this unit in the megapascals. Right now, it's on top in the numerator, which means over here, it must be on bottom in the denominator. Because now, as the math folk would say, it is going to reduce to 1 and effectively is going to be removed or canceled out, quote unquote, is what's going to happen here. Well, next, in this upper right-hand box, this is the unit that we're trying to get to, which is bars, because we need to then do a comparison between the two. Now we're ready to plug in what is our unit conversion, match the numbers with the units. The 10 goes to the bars. The 1 goes to the megapascals. Now we've set up our unit conversion properly. Any numbers that are on top, multiply. Any numbers that are on bottom, divide. So we really need to multiply by 10. Dividing by 1 is kind of redundant, but we do need to do this multiply by 10. So rules of 10 say when you are multiplying, count how many zeros there are. There is 1 0. Move the decimal place 1 time. The number should get bigger by a decimal value of 1. So we need to move this to the right. So we get negative 1.5. MPa is gone. We're left with, don't forget our unit, bars. Now, if we compare, it said the same cell as before, which means this negative 4.0, you're gone. So we changed the solution, but the same cell, the negative 1.5. Now the environment also has a negative 1.5 for its water potential. Since the two of these are going to be the same, this is an isotonic solution, so there is no net movement of water in this case. As the final of this question says, which direction will the net flow of water be? Nowhere. It's going to move in and out at the same rate, so there's no big push internally or externally. Next up, for question number 4, well, we'll do 4 and 5. We'll wrap it up there. It says here for 4, the value for the water potential in a root tissue. Now we're talking about plants. And it actually gave us the water potential, which is super nice. I'm going to go ahead and actually I'm going to clean this up. I'm going to reset our little cell. I'm going to leave the beaker though. I'm going to reset that. Okay, so we know that the water potential in the cell, negative 3.3. Okay, great. Now it's going to ask us, I'm going to imagine here that it's going to ask us what is going to happen in the environment. Actually, I do need to fix the cell. All right, we're good. If you take the root tissue and place it into, we have a 0.1 molar, which is a concentration, of sucrose here. So this is one of our sugars. If you recall, I believe I mentioned in class and possibly in our notes as well, we have any one of our sugars, when it's dissolved in water, it produces 1 ion. So the I value is going to be 1. So it will not dissociate and separate into multiple ions. It will dissociate, well, not really dissociate, but it'll dissolve and form 1 ion. So the I value is 1 for our ionization constant for all of our sugars. It says it's at 20 degrees Celsius, but again, we don't want Celsius. We want, according to our negative I crit, you can kind of see where we're going with this. We need degrees Kelvin to do the conversion. Take your degrees Celsius plus 273, and now you get your degrees Kelvin, which will get to 293 degrees Kelvin. All right, keep going. In an open beaker, there's that open beaker thing again. So we know that the pressure potential is going to be 0. Because again, it's in an open container sitting on your counter or whatever. So the pressure potential is 0. What is the water potential of the solution? And additionally, what direction will the net flow be? So really what we need to do, because we know the pressure potential is 0, we really need the solute potential. And we're going to use our negative I crit here to then calculate this value. So let's start with the negative. We said that I, the ionization constant, again, because it's a sugar, they do not dissociate. It's just going to produce 1 ion, or 1 charged particle, rather. In this case. Next, we need to multiply by the concentration. That's our 0.1. Next, we have to multiply by our R value, 0.0831. Last but not least, our degrees temperature in Kelvin, which is our 293. Now, if we plug all this into a calculator, be careful of the negative that's in the beginning. You must factor that in. So negative 1 times 0.1 times 0.0831 times 293, we should get to our solute potential in this case is going to be negative 2.43, we'll say. We'll stop there. Negative 2.43. Fantastic. To back up real quick, because our pressure potential is 0, this is not going to factor into the water potential. The water potential is the solute potential because, again, pressure is 0. So we have in the environment is a negative 2.43. Who has the higher water potential and who has the lower water potential? Be careful again, it is negative values. The closer to 0, the higher the value. So the environment or the solution here is going to have the higher water potential. So it wants to go from high to low. So water in this case is going to want to flow into the cell. So this would be a hypotonic solution, causing water to rush into the cell compared to the cell using our water potentials. Alrighty. Number 5, we're going to basically do the same exact thing, but the only thing we're going to change is that instead of glucose, 1 ionization constant, now we're using sodium and chlorine. We have our table salts, some sodium chloride, and it even tells us it dissociates into 2 particles. So our I value in this case is not going to be 1, it's going to be 2. If we keep going, it says that we still have our concentration 0.1, instead of our sucrose. So the number for the concentration did not change. What we dissolved, the solute, then changed. Everything else is going to be exactly the same. Nothing else. The temperature is the same. Our R value is going to be the same. Concentration is the same. So basically, we can use the same equation that we did last time, but instead of a 1, I'm going to swap that out. It's going to be a 2. So we're just going to change one number. And basically, it's going to take that negative 2.43, we need to double it. So what we get instead, our solute potential for question number 5, negative 4.86 is what we get instead. So our environment changes from a negative 2.43 to a negative 4.86. Now, once again, we compare who has the higher water potential, who has the lower water potential. Again, they're both negatives. So the closer to 0 you get, the higher the value. So this negative 3.3, that is going to be our higher value. So I need to fix the cell, actually. Here's our cell. Here's a wavy line. Great. So our cell, we said, was negative 3.3. The environment, or the solution here, is a negative 4.86. So the water is going to want to rush from the higher, that's the cell, to the lower, which is the environment. Now we have a hypertonic solution, and water is going to want to rush out of the cell, is going to be the net flow of this direction. I hope this helped, kind of got you started. Please let me know if you have any additional questions. I'm always available in our office hours, or you can drop into class anytime and ask some questions. Thank you all for watching. Have a fantastic day.